Hello.
Good morning.
Good morning. How are you?
Good. How are you?
Good. Do you have office hours on Tuesday?
Yes.
Because I need help with uploading my programs into the internet.
Okay.
I have like 4 or 5 of them done, and I cannot get it into internet.
Sure. So next week?
And next week Tuesday. I'm working on 2 more right now, so I'll have everything done.
And remember, we also have our lab assistants and tutors, and they can help as well.
I'm meeting with. I'm like during their time I'm working, so I'm meeting with one of them on Friday. Hopefully, if he can help me, great. If not, I'll come on office hours on Tuesday.
Okay, great. We got a small crowd here today. Maybe some more will
Is
come
my microphone normal?
It sounds normal this time.
Okay, good.
It's the physics class, I'm telling you.
Is it killer?
It is.
Oh. Which one is it?
Well, I have the 110 and the lab, and like lab online, it doesn't really help.
So it's just a lot of work, and
it's a lot of work, and then a lot of formulas, and and he doesn't grade really easy either.
Oh, yeah, that can be tough. Well, hopefully you got a chance to watch the video from Tuesday, and you're kind of caught up on doing sorting of arrays. So we're going to take those 3 arrays that we had last time, the array of floats, the array of strings, and the array of structs, and we're going to learn how to search them. We did that last week by doing a linear search. It would start at the beginning of the array and then scan through the array until it found what it was looking for, and then it would display what it found. Or if it got all the way through the array, then it would say that it couldn't find it. But if you have the array sorted, then you can do the searching much more efficiently. Let's see if I can give you an example of that. Let's start with this here. So I have here 7 cards that are kind of obscured, and the goal is to find the number 20. Now, I'll tell you here that the array is not sorted, and so in order to find that number 20, you pretty much just have to kind of punch away at random until you find what you're looking for. There it is. So in this case, it took 5 tries to get to the number 20. I'll try again. So since the numbers are not in any particular order, really, the best strategy is just to start at the beginning and go until you find what you're looking for. But if the array is sorted, you can be more intelligent about it. So here we're looking for the number 44. We can start at the middle. And then since we're looking for the number 44, it must be to the right in this case. So what we're looking for is bigger than 32. So we'll split that range of 3 in half. And there, we found it in 2 tries. Let's try again. So we'll start in the middle. Then we'll go to the middle. Oh, found it there. It must be over here and then here. So with 7 unknown numbers, an array of 7 numbers, what's the most number of tries that it'll take for me to find what I'm looking for?
3.
3, right? It'll take at most 3. With the unsorted array, it could take as many as 7. I could start at the beginning and then go all the way to the end. So with this thing called a binary search, it's only going to take at most 3 tries to find what we're looking for. We could get lucky and find it in the first one. So if the array is sorted, we can do a binary search, and then it's much faster. A question for you would be, if we had 100 items in the array, how many would I have to look at?
The minimum or the maximum?
Maximum.
So it's going to be 100 divided by 2. That's going to be 50.
Mm-hmm.
And then 50 divided by 2, 25. 25 divided by,
12 and a half,
25.
but then round up. So we'll go 13. And then divide that by 2, but round up.
That's going to be 7.
7. Mm-hmm.
And then 3.
We'll go 4.
4.
Yeah.
And then 2.
And then 2. And then the 1 that we're looking for.
So 1, 2, 3, 4, 5, 6, 7, 8.
How about if we had 500?
So that's going to be 250. It's 125.
Mm-hmm.
62.
We'll go 63.
63.
Mm-hmm.
And then 31. 32. 31. And then
32 would be better. Yeah.
32. It's going to be 16, 8, 4, 2, 1.
So it was a total of, so how many, so
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
10, yeah. So it'll take at most, well, so this number 8 here is actually 1 more than it should be, because what we really need to calculate is how many times did we divide it in half. We divided it in half 7 times.
7 times.
And here we
and
did
then 9 times.
9 times, yeah. So this is what we started with, but every time we look at one, we divide it in half. So really this is 7. And this is actually 9. So we're able to have an array with 5 times as many elements in it, but it takes us only 2 more looks, 2 more checks to find what we're looking for. And if we go up to 1,000,
That's going to take 1 more only.
it's going to take 1 more, yep, because we just double from that one. Right?
Yeah.
And if we have, in our case, 100,000,
That's going to be,
so it's going to be the log base 2 of 100,000.
okay.
And then round it up. Let's see, what is that?
$500? No, 50.
Google's calculator says that is 16.6. So when you use LG, that is taken as meaning the base
2.
2 logarithm. If you use LOG,
That's a 10.
that's base 10. And if you use LN,
That's
that's
10.
base E.
Oh yeah.
So 16.6, but you round that up and you get 17. So we're able to do 100 times as many in only 7 more. So this gives us a big win over doing a linear search. So last time we started with this program, which generated an array of 100,000 random floating point numbers, filled up an array with them. And then we called qsort right here. Qsort, you give it the array you want to sort, how long it is, how big each element of the array is. In this case, it's an array of floats, so each element is a float size. And then a function that's going to be used to compare elements of the array and tell it whether those elements are in the correct order or need to be switched. This function, which we called fcompare, needs to return a 0 if the two elements are equal to each other, a negative number if the first element is less than the second element, and a positive number otherwise. So you're passed in pointers to two elements. I called them A and B here. We need to cast them to be the correct type because they come in as void pointers, which means they're just generic pointers to something. We need to cast them to be the correct thing, in this case float pointers, and then we dereference them. And if they're equal to each other, return a 0. If this one is less than, return -1, otherwise return a +1. And we discovered last time that if we have an array with 100,000 floats in it, it took about 20-30 seconds to sort it using bubble sort, but it was nearly instantaneous using quicksort. So this time, after sorting the array, we want to prompt the user to type in, let's say, a number to search for, and then it will go and find it. Now, I got a little problem here in that I don't really know like what's in the array because it's just an array of random numbers. I think what I'm going to have to do, see, if it's going to prompt me for, this is the problem, if it prompts me for a number to type in, I'm going to type in some like random floating point number, and it's going to say it's not there because the chances that it's there is like really small. So I think what I'm going to do here is I am going to make still 100,000 random numbers, but I think what I should do is maybe a smaller range, like from 0 to 100, and also maybe, no, I know what I can do. Still going to be a bigger range, but I'll just turn them all into integers, but store them as floats, right? So it's going to be like, instead of like 557.25, it'll just be 557.0. I think that might work out a little bit better. So we're going to take our random number, divide it by 10,000, and then we'll convert that to an integer, and then we'll convert that back to a float. Let's just make sure this works. So this is what I'm looking for. A whole bunch of whole number floating point numbers. This will make it easier to find something. Okay, so right in here, let's prompt the user. Oh, let's have it save the array. And let's prompt the user here. And now if we were doing a linear search, we would start from the beginning of the array and go to the end and try to find it. So let's go ahead and put in a, let's see, float found equals linear search of the array and its length. And let's also pass in the target that we're looking for. So we're going to search for a target out of this array of this length. And I think what I'm going to do is I'm going to do it like this. I'm going to return a pointer to what it found. And I'll say if found, so if I got a valid pointer back, then I can go ahead and print it out. Found %f. Otherwise, print out a message to say I didn't find it. Okay, now I just need to write this linear search function. Let's put that function, I guess, down at the bottom. Okay, so we need to start at the beginning of the array, go to the end of the array. And then we'll say if a bracket I is equal to our target, then go ahead and return the address of what we found. And then if we got all the way through the array and didn't find anything, we'll return null. Okay, so our function here returns a float pointer. It takes in a target to search for, an array to search through, and how long the array is. It loops from 0 to size and then looks at the ith element of the array. And if it's equal to our target, go ahead and return the address of what we found. Otherwise, return a null. Oh, I need to declare something. I think that'll fix it. There we go. All right, what to find? Let's search for 1, 2, 3. Didn't find it. Let's try it again. 1, 2, 3. Didn't find it. Uh-oh. We got to solve a problem here. 585. Oh, okay, we found that one. So it took a while, but we were able to actually find what we're looking for. Are we good so far? So that's linear search. Starts at the beginning of the array, scans until it finds what it's looking for, and then returns what it found. So let's replace that linear search with the built-in binary search function. So the built-in binary search function works in a very similar way. It still returns a pointer to what it found. You pass in 5 parameters this time. You pass in the thing you're looking for, which is our target. Actually, let me bring up the documentation for it. Okay, so you pass in a pointer to the thing that you're searching for. Okay, that's one important thing. A pointer to the thing you're searching for, the array to search through, the number of items in the array, the size of each element of the array, and a comparison function. So 5 elements. The first one is going to be a pointer to the thing we're searching for. And then we've got the array, the length of the array, the size of each element of the array, and then a comparison function. Okay, so we need to search for a pointer to the thing we're searching for, the array, which is ARR, its length, size of float, and a comparison function. And in this case, you can't use the same comparison function that we did for sorting. For sorting, we were passed pointers to 2 elements of the array that we're sorting. This comparison function is still going to take 2 parameters, but the first parameter is the thing we're looking for, and the second parameter is one of the elements of the array. So we can't use the same one because it takes different parameters, even though in the documentation it looks like they take the same parameters. They're still both void pointers, but in this case the comparison function takes in a pointer to the thing you're searching for, and the second parameter is one of the elements of the array. So we'll call this bsearch, right? Because we're searching through floats. And then this part works the same. You still get a pointer back to the thing that you found, and then you can dereference it to see what it actually did find. All right, so let's go write that bsearch. So int bsearch const void pointer t for target and const void pointer e for an element. And I think I'll just do it right here. So this should return 0 if the thing that t is pointing to is equal to the thing that e is pointing to. Return a negative if the thing that t is pointing to is less than the thing that e is pointing to. And return a positive number if the thing that t is pointing to is greater than the thing that e is pointing to. So same kind of return values from the comparison function for binary search, but remember this takes different parameters. Okay, the first thing to do is to cast t and e to be the correct thing. They're passed in as void pointers, but we need to cast them to be what they actually are. In this case, t is going to be a pointer to a float, which is our target float that we're looking for, and e is also going to be a pointer to a float because it is one of the elements of the array, which is an array of floats. Oh, I am missing the function declaration. And now we can kind of do the same thing we did here. We're going to dereference TT and see if it's equal to dereferencing EE. And if it is, return 0. If it's less than, return a negative number. Otherwise, return a positive number. And in a minute or two, after we verify this is working, we'll go ahead and clean up this function so that it's a little bit neater. But this is basically what it's going to look like. All right, let's try it out. Oh, I'm missing a return here. Now we're just going to have to kind of keep trying. Ah, there we go, until we find it. Because the array is made up of random numbers, I don't know whether a specific number is in there or not. So what we could do, actually, is we could run the program. We could look at our output file and scan here for something to search for. Let's say this one, 145917. And it should say that it found it, because it's right there. And we could also run it again, and now we have to scan here for something that's not there, like 146000. That is not there. Okay, so that is binary search. You pass in a pointer to the thing you're looking for, the array, the length of the array, the size of each element of the array, and then a comparison function. And it returns a pointer to the thing that it found. Dereference that, and then you can see what's in there. The comparison function, you pass in two void pointers. The first one is the target, and the second one is an element of the array. We need to cast them to be the correct type of thing. So the target is a float pointer, and the element is also a float pointer. And then dereference them and see whether they're equal to, less than, or greater than. So here's the first cleanup we can do. And this is actually a big one here, is if the thing I'm looking for, let's say the number 10, is equal to the element that I'm pointing at, and let's say that's also the number 10, then I want to return a 0. If the thing I'm looking for, let's say 15, and the thing that I'm looking at, which is the 10, if the 15 is greater than the 10, I want to return a positive number. And if the thing I'm pointing at, let's say it's 5, is less than the 10, then I want to return a negative number. So instead of doing these comparisons, where I see if it's equal to, greater than, or less than, when I'm dealing with numbers, what I could do is I could just subtract the two numbers. Okay? So if the target is 10 and the element is 10, and I subtract them, I get 0, which is exactly what I want to return. And if the target is 15 and the element is 10, and I subtract them, I'll get 5, which is a positive number. And then finally, if the target is 5 and the element is 10, and I subtract them, I'll get negative 5, which is a negative number. And that's exactly what we want. So we can actually clean all this if-else's up and just do a subtraction. And let's go ahead and try this out. First, let's look for something that is in there. 146101. And it found it. And let's run it again, and let's search for something that's not in there. Like 145849. That's not there. So this is way easier than doing a chain of if-else's. You just subtract them. This works for numbers. Just subtract them, and you'll get the kind of return values you're looking for. And we can also clean this up by integrating the casts into here if you wanted to. So let me compile that and run it. And let's search for something that's there, 145751. And it's there. So here I just took the casts that I had before and just slipped them right into the expression itself. We could do the same thing up here for this F compare. We could just say return, and then a subtraction right here, and then take out these if-elses. Let's make sure that still works. 145825. Good. And then run it again, and we'll search for something that's not there. 145770. That's not there. Good. So let's scan through this entire program from beginning to end. So we start by defining a length to be 100,000. Here's all the functions we have. We have one called make array, save array, sort array, F compare, linear search, and F search. F compare is used for sorting, and F search is used for searching. In our main, we call make array. We pass in the length, and it returns us an array of that length. And then we sort it using qsort. Pass in the array, its length, the size of each element of the array, and a comparison function. Then call save array in order to write it to a file. Prompt the user to search for a target, and then call bsearch. You pass in a pointer to the thing you're searching for, the array, the length of the array, the size of each element, and a function to compare target to element. And then if you got back a valid pointer, then you found it. Just dereference it to see what's inside. If you got back a null, then you didn't find it. Here's make array. It seeds a random number generator, uses malloc to create an array of that given size, fills it with random numbers, in this case random integers that are stored as floats, and then return the array. Here's save array. It opens up a file called out.txt, and then writes the array to the file and then closes it. Here's bubble sort on the array. Two loops. This is a size -1 passes through the array, and then size -1 comparisons of pairs of values. And then if they're out of order, simply swap them. And then finally, our linear search that goes from 0 up to the size of the array, checks to see if we found the target, and if we did, return the address of what we found. And I did it like this in order to match the style of the way that bsearch works. And then return a null if we got all the way through the loop and we didn't find what we were looking for. So that's the program. So let's go ahead and do it with sort string. This is the one that loads in a bunch of words into the array, sorts it, and saves it. Let's go ahead and compile it and run it. And we can see that this now contains a whole bunch of words. So we're starting with a file that has 3 million words in it, and we're pulling out the first 100,000 of them. We saw last time that when we call sort array using our bubble sort, it took on the order of, well, actually, I think for this one, for the strings, we let it run for about a minute, and it was never able to finish in that minute. But then when we replaced it with qsort, it ran in less than a second, probably even about 1/10 of a second. So it's a huge, huge speed up. So we're going to do kind of the same thing we did for the other one. We're going to prompt the user to type in a word to search for. I'll just use scanf for this because I just want a single word. And also scanf will chop off the new line for me. And then, should we do a linear search or should we just skip straight to binary search? What do you think?
Linear is going to take longer, though.
It will, because now we're doing string compares. But do you want me to write a linear search function, or
Sure.
should we go
Yep.
straight for, all right?
We can do both.
So we'll do character pointer found equals linear search. We will pass in a pointer to the thing we're searching for, so the address of target, the array we're searching through, which is ARR, and its length. I guess actually, since they are strings, why don't I just pass in the target? And then since we're going to return strings, I will just return the string that we found. Okay, and then if found, printf found %s. Otherwise, print out that we didn't find it. Okay, let's go write our linear search. We're going to pass in our target, our array, and since it's an array of strings, it is a character pointer. All right, so we're going to go for int I equals 0. I is less than size. This is the same as the one we did before. And now if string compare, the element of the array and the target is equal to 0, then return the address of what we found. Oh, in this case, we're just going to return a character pointer, so we'll just return the thing that we found. And if we got all the way through the loop and we didn't find what we were looking for, we'll just return a null. Okay, so this is basically the same function that we did linear search for the floats, but in this case, we're using string compare to see whether the element of the array and the target are the same, and if they are, just return the element of the array that we found. Okay, what to find? Password. I know that's in there. Found it. What to find? Jumble of letters. Didn't find it. What to find? Rock you. I know that's there. So, seems to be working. So that's linear search. This one seems to be pretty quick because we got 100,000 words in there. But to look at 100,000 words, it only takes at most 100,000 string compares. Remember, sorting took up to 10 billion string compares. So doing linear search is still pretty quick, but doing binary search on it will be faster. It's just hard to measure it because it's still pretty quick. You know, one way that we could measure it, or perhaps measure it, is let's increase this to 1,000,000. Oh, it's still pretty quick.
Yeah, you can't really tell the difference.
No, but what I did notice was that the sorting took a moment to do. If I run it again, you'll see that there's a little pause between when I run the program and when it prompts the user to type in a string to search for. So during that half second or so is when it's doing all those sorts. We got 1,000,000 entries in there, so it's taking roughly 1,000,000 times the log base 2 of 1,000,000, which I think is 20. So about 20 million comparisons. And then it has to write that to a file, which is also taking some time as well. Okay, so let's take out this call to linear search and replace it with a call to bsearch. So we're going to pass in a pointer to the thing we're searching for, which in this case is just the target because it's already a pointer. It's a string, so we're already passing in a pointer to it, so that's fine the way it is. We're going to search through the array, its length, and then we have to tell it how big each element of the array is. In this case, each element of the array is a character pointer. And then finally, a function that's used to compare the target to the elements. Let's call it ssort. And what we're going to get back from binary search is a pointer to the thing that it found. So it's going to return a pointer to one of the elements of the array. And each element of the array is a character pointer, so we're going to get back a pointer to a character pointer. So we just need to write ssort. Or, sorry, not ssort. What did I call it? Search. String search. Still passing the same parameters, const void pointer t and const void pointer e. And then we need to cast them to be the correct thing. So t is the target string that we're searching for. It's being passed in as a character pointer. So we just need to cast it to be a character pointer. And E is an element of the array. Each element of the array is a character pointer, so E is actually a pointer to a character pointer. So this is an instance where the cast for the target and the cast for the element are different because they're pointing to different things. But ultimately, they're both strings, so we just need to call string compare and return what it returns. So string compare needs a character pointer and a character pointer. Two strings. T is already a character pointer, or TT. TT is already a character pointer, so we can pass that in as is. E, however, is a pointer to a character pointer, so we need to dereference it in order to convert it back into a character pointer. Someone's asking here, is there a way to find out how long it took to find? You know, what we could do is we could put in a global variable, and every time our comparison function is called, we could increment that number and then print out that number. Would that work for you? Why don't we do that after we finish this here? So every time our comparison function is called, we just increment a global variable, and then we can just print out that value of that global variable. Okay, so down here, binary search returns a pointer to the thing that it found, so a pointer to a string. So in order to print out what we found, we need to dereference it because we need to pass in an actual string, not a pointer to a string. So that's the only difference that we have to do here. So found password. Let's try it with a jumble of characters, and didn't find that one. We're doing 1,000,000 here, that's right? Yeah. So it looked like it slowed down a little bit, but we can try this again. Seems to be working. So let's go ahead and try what you suggested. Let's make a global variable here. Int now, do you want to do this for the search function or the comparison function, or both? I guess we might as well do both. Let's do bsearch count and bcompare count. So we'll just do both. So bcompare will return bcompare count plus plus. Oh, we'll return those. We'll just increment. And then inside of bsearch, we'll do bsearch count plus plus. And then finally down here, we'll print that out. And then when we do the search here, right here, we will print out search comparisons. Okay, so to sort our array of 1,000,000 strings, it took, let's see, 12.5 million comparisons, 12.5 million calls to string compare. And let's see what that should have been. So if it is truly a n log n quicksort algorithm, it should take 1 million times the log base 2 of a million, which is 20, I believe. Let me bring that up here. Log, so 1, 1, 2, 3, 1, 2, 3 times the log base 2 of 1, 2, 3, 1, 2, 3. Did I get that right? 1 million. Trying to count the zeros here. Let's just bring it so it's bigger here. 1 million, oh, this is 100,000, so that needs to be, how can I edit this? Can I? No. So according to this, it should have been, yeah, about 20 million. But here, according to this, it took about 12 million, and that's probably because the array wasn't like truly in a completely random order. In fact, there are parts of the array that are already sorted. If we were to scan through the actual file, we would find there are significant sections of it that are actually already sorted. The first few thousand entries are more or less in a random order, but then once you get beyond that, it starts being sort of an alphabetical order. So that's, I could see why there might be slightly less comparisons that's done, because some of it's already in the correct order. And then we'll search for what to find. And in this case, it took only 19 comparisons to find password out of 1 million of them. And if we search for something else like rock U, only 17 comparisons for that. So that is a huge, huge difference between searching through up to 1 million entries in order to find what we're looking for. In this case, it looks at only about 20 or so. In fact, I believe 20 is the maximum, maybe even 19, to find what we're looking for, because we have 1 million entries, and it would take only 20 halvings to get down to 1. Let's see, let's search for something else, like aardvark. So it took 20 comparisons to find that. Okay, so let's quickly go through this file. We've got our length. In this case, we made it 1 million. We've got these two global variables to keep track of how many comparisons we did. And then our functions. We've got scompare, which is comparing pairs of elements in the array. And just use string compare to do that. And then bsearch, which also just does comparisons of elements in the array, but in this case, the target and one of the elements in the array. And you can see here that the way we do the cast is different because we pass them in slightly differently. For our main, we create the array, sort it using qsort, save it to a file so we can see what's in it, print out how many comparisons it took. And then we search for a target, call bsearch. We pass in the target, the array, its length, the size of each element, and then a function to do the search comparisons. Then we print out how many comparisons it took, and then print out whether it was found or not. Here's make array. It allocates an array of character pointers, opens up the rocku file, and then reads in up to the number of words that we're looking for, in this case the length, allocates space for each one, copies them in, attaches it to the array, returns the array. In this case, I don't need to return the length because I already know what the length is, because I have it in a define up at the top. Save array just opens the file for writing. This is pretty much the same as the save array from the floating point example, but it's just outputting strings instead. And then this is the bubble sort for strings. It just uses string compare instead of less than or greater than. And then finally, linear search. Okay, Any questions on that? So we had one more example that we worked on last time and the time before that, which was this Pokédex. So this one keeps track of some Pokemon. There are 7 Pokemon we've got in there. We've got their name, hit points, and what type of Pokemon they are. So that's all stored in a struct that contains their name, hit point, and what type they are. We have a load Pokédex function that takes in the file name and how many entries in that array there will be when it's done. And it returns the array, and it also returns the size in this variable here. We've got search Pokédex that does a linear search. So we load in the Pokédex, sort it using qsort, and then print it out. So we are going to uncomment this section and it has our linear search in there, and let's just verify that it works. Oh, I'm in the wrong directory. So let's search for Pikachu. And it says it found it. So when we do our search Pokédex, we pass in the Pokemon we're looking for. In this case, it's just a string. The Pokédex array and how long it is. And then we're doing a linear search. So here's our linear search. We're passing in the string that we're searching for, the array of Pokemon, and its length. And then we're using string compare to compare the target string against the name inside of those structs. And when we find it, we return a pointer to the struct that we found. So let's replace that call, that linear search. I'm going to change this comment. Search for target Pokemon. Let's replace that linear search with our binary search. So we are going to get back a pointer to a Pokemon. So just like our original search, we're going to get back a pointer to a Pokemon. We're going to call bsearch. We're going to pass in the thing that we're searching for, which is our target name, the array we're searching through, its length, the size of each element, which is a Pokemon structure, and then our comparison function. Let's call it bsearch, Pokemon search. And then if we got a valid Pokemon back, then we print out found and then print out the Pokemon. Otherwise, we print out that we didn't find it. Okay, so let's do our bsearch function. So we're passed in a target and an element. The target is a string, and the element is a pointer to a Pokemon. So let's do the correct casts here. T is a string, so it's a character pointer. So we'll cast it to a character pointer. And E is a pointer to a Pokemon. And since we are searching names, we can just use string compare. We're going to compare the target name to the name of the Pokemon that we are pointing to. So that's going to be EE pointer name. EE is a Pokemon pointer, and so we use the arrow notation to get to the field that we're looking for. Great, we found a Pokemon, found a Pikachu, and if we search for one that's not in there, then we say, didn't find it. So for this bsearch function, we're passed in a string and a pointer to a Pokemon. And so the casts look very much different. Contrast that with the cast that we did for sort float, in which they were both float pointers, but one was the target and one was an element of the array. So the casts ended up being the same. And then in sort string, the casts were a little bit different. The target is a string, and the element is a pointer to a string. So one is a character pointer, and one is a character pointer pointer. But for the Pokemon, the casts are very different. The target is a string, it's a character pointer, and the element is a Pokemon pointer. So it's very important to maybe draw a picture of what your array looks like and be very clear on what those elements are. If each element is a Pokemon, then your search function is going to be passed a pointer to a Pokemon. If each one of those elements is a character pointer, then your function will be passed a pointer to a character pointer. So you just have to make sure you're doing the casts correctly. So are there any questions with that? So I wanted to show you 3 different types of arrays. We've got arrays of numbers, arrays of strings, and arrays of structs. And in this case, we're searching those structs by name, and we're sorting the structs by name. So when you have a struct that has several fields in it, you need to decide which of those fields are you going to use as the key, as the index for sorting. And you know, you could get fancier here. You could do something like, if the names of the Pokemon are the same, then you could use something else to decide how to break the tie. So, yeah, I don't know if, like, I don't have my son's Pokemon Pokédex book here anymore, but is it possible that you could have a Pikachu with a hit point of 60 and a Pikachu with a hit point of 80? If that's the case, how would you sort those 2 Pikachu? Would you sort the 60 first and then the 80 next? Or would you just leave it in a random order? The way we've got it now, it'll just kind of go in a random order because we're only looking at the name. But we could do something like, let's see, how would we do this? We would do like, if the string comparison is equal to 0, which means the 2 names are the same, then we need to go ahead and break the tie by looking at their hit points. And this is almost one place where I'd prefer to do the casts first in separate lines, so I don't clutter up all this stuff with all these casts in there that kind of confuse things. So if the names are the same, then compare their hit points. If their names are different, then we should just return whatever this returned. So I think just for keeping things a little bit simpler, so I don't call string compare again. What I'll do is I'll go like int compare equals, and then I'll call the string compare right here. I'll do like that. And then I'll say if what I got back is equal to 0, I'll go ahead and return the hit point comparison. Otherwise, I'll return whatever string compare returned. So let's go and put in another Pikachu with a different hit point. Let's put in 70. And maybe another one, just to show that it's working, with fewer hit points. And when we see it sorted, it should come out so that it's a Pikachu 30, then Pikachu 60, and then Pikachu 70. Uh-oh, something happened. It came out 60, 70, 30. Let me look at my, oh, I don't write a file, do I? So what happened there? It came out 60, 70, 30. Now let's go and debug this. Okay, so I do a string compare of A's name and B's name, and if the comparison came out to be 0, which means that the names are the same, then I should go ahead and return A's. Oh, I see. I did A here. I did A over here also. So I should have done B. That's the problem. There we go. So now the Pikachus are in the correct order. So your comparison functions can be a little more fancy than just simply looking at one of the fields of the struct. You can look at multiple fields of the struct and decide how you're going to sort them based upon the values of those fields. Let's see, someone asked here, would it be fair to say that your coding is in a functional paradigm? You know, I tend to kind of do that. I do have some experience with functional programming, and so I guess I tend to kind of incorporate some of that into my procedural programming, like C and Java, where I start by writing functions that generate a data structure, and then write additional functions that kind of filter through it or transform it until I get it down to what I want. So I might start with a function that reads in a whole file, and then write another function that filters through that file and returns just the ones that I want, and then write another function that filters through that or maps that onto something else. So I think about it in terms of how is the data flowing through my program, and what kind of transformations can I make to the data along the way as it's going. And it really helps to make the program more modular because you are now inputting data structures and outputting data structures. And that means you can potentially mix and match the components. Right? I can decide not to sort them by just commenting out the line that sorts them. I can decide not to search them by commenting out the section of code that does that. So that's why I don't like read the array in and sort it as I'm going. I read the whole array in and then sort it later on. Another question is, could we replace the if statement with a Boolean comparison so that if it's 1, so that it is 1 if the name and the hit points match. So if the name and the hit points match, then we actually want our function to return a 0, which means that those two Pokemon are exactly the same. So this should return a 0 if the two Pokemon are identical, at least as far as we're concerned. And by identical, meaning their names are identical and their hit points are identical. Doesn't matter what their type is. So certainly we could replace this with a Boolean that returns a 0 if they are not equal and a 1 if they are equal to, but then that kind of, it does two things. One is it takes our comparison and boils down to two values, either 0 or 1. So there's two problems with that. One is the 0s and 1s are flipped from the way they should be. 0 should mean they are equal, and 1 means they're not equal to. So we have to flip that. And the other is the function needs to return three values, a positive value, a 0, or a negative value. And by just having it return either a 0 or 1, we've taken it boiled down to two values. And it needs those three in order to know whether to keep the two elements the same or to switch them. And if you just return a 0 or a 1, indicating that they're the same or not the same, it's not going to know whether they're in the correct order or not. So if they're not the same, it needs to know whether to keep them in the same order or to switch them. So I guess I was thinking here, is there a way for me to boil this down to just like one return statement that happens to work? So if the string compare returned a 0, then go ahead and do this one. But if it returns something other than 0, don't do this one. You could probably do that with some short circuit evaluation. But the short circuit evaluation depends upon 0 being false and 1 being true. And in this case, we need 0 to be true and 1 to be not true. So I'm not sure if we can get away with that. Still, it would be kind of an interesting thing to try. So this is what I wanted to show you today, is how to do all of these different kinds of searchings. For the people who are actually in my class, we do have an assignment to do. So I think what we're going to do is take a little break, 10 minutes or so, and then when we come back, we'll go over that assignment.
Okay.
Next week is, in the United States, a holiday weekend. Thursday's a holiday. Now, a lot of our high schools and elementary schools get the whole week off. So my kids will be here, but our college does not get the week off. We only get Thursday and Friday off. So we will be streaming as usual on Tuesday. I think we'll spend that day kind of going over debugging this assignment. So try to get started on it over the weekend, and then we can come back on Tuesday and start working on getting some of the bugs out. It's not due until the week after we come back from break. So we'll spend some time debugging it, and then we'll also start introducing networking so that we can write C programs that communicate with other computers. So let's take a little break. I'm going to pause the Zoom recording, but the YouTube recording I think will just keep going, and then when we come back, we'll do a quick overview of the assignment.
Recording stopped.
How do I deal with multiple files search? Well, do the files contain different things, or do they contain the same things? Like, does one file contain, let's say, information about Pokemon, and another file contains information about trainers? And if that's the case, then you need two different structs for each one, and therefore you need to have different sorting functions and different comparison functions. Now, if they were just multiple files of the same kind of things, like you had a file containing some words and another file containing some words, then it would just be a matter of reading all of those files into the same array and then sorting them. If that's what you want to do, if you wanted to merge everything together. If you didn't want to, you didn't merge everything together and you just wanted to search one file and then the next file and the next file, I guess one way to do it would be load the first file into an array, sort it, search it. If you don't find what you're looking for, load the next file into maybe the same array, just overwriting all the values. Then sort it, search it, move on to the next one. Alternatively, you could read all the files into separate arrays and then sort them all separately and then search them all separately. But because they are the same types of things, let's say they're all strings in all the different arrays, you can recycle or reuse the same comparison functions and the same searching functions. So those don't change. And then, gosh, if you had a bunch of files, let's say you had hundreds of files, well, now you're essentially doing a linear search, right, through all these files. You're starting with the first file, and then the second file, and the third file. You're doing a binary search within each file, but a linear search through all the files. And, you know, that's going to be pretty easy to do, but if you had hundreds or even thousands of files, you know, maybe now you need to do something more intelligent, like pull all the files into one giant data structure, sort the whole thing, and then look for what you're search for what you're looking for, and that might be more efficient than doing a linear search through all the different files. I guess it really depends upon your application and your use case. Is it more trouble to spend the time building a giant data structure? I mean, if your developer time is worth money, let's say, well, in the United States, a programmer might start out at $40 an hour, let's say, maybe a little bit less, but let's say it's $40 an hour. If you can type up a solution that does a linear search through all those files, but a binary search within each file, let's say you can get that all cobbled together in 2 hours, then that's costing your employer $80. So $80 to do that search, and then you're done. And then let's say this is something you only have to do once, right? So it takes 2 hours of work, and then you're done. And let's say it only takes a minute to run the program to do all those searching. But then you can say, like, well, I can be smarter about that. I could build a data structure, or I could read all those files into one large data structure. Then let's say it takes another hour for you to do that. So now it takes 3 hours of work, but your program runs in 10 seconds instead of a minute. Was that worth the extra effort? You know, it cost your employer an extra $39.95. So sometimes you just have to balance how much work it's going to take you to implement a solution that's running faster. Now, if you have to do this, let's say 1,000 times a day, where you have to run this program where it's got to search through thousands of files, all the files are large, then it might be worthwhile to spend the extra time to do something more efficient. But if you're only going to do this a few times, come up with a solution that is the cheapest, I would say, in terms of your hours. Because developer time is probably the most expensive expense, right? $40 an hour to pay a person to do the work, versus virtually nothing for the computer to actually perform the work once it's been done. Oh, there's a good suggestion. Maybe just throw everything into a database, and then and there the database already does really efficient searches. So if you're handy with databases and you can cobble together a table to hold the data you're looking for and load everything in pretty quickly, then maybe it only takes you 20 minutes to implement that solution. That's way cheaper. And you know what? There's even some solutions that are slower, but way easier to get going. There's someone suggested using like SQLite or DuckDB, which is probably really lightweight databases that you can get going pretty quickly. You don't have to fire up a database server and permissions and things like that. You just simply point your database library at your files and then it uses them. Or you write a program to load the data into these databases, and then you just point your libraries at this existing file that holds your data. There's also another library that I use quite a bit. It's a command line program called Q. It's just all, and actually the package manager I think calls it text files as data. I think that's the name of the package. And what it is it's a SQL-like engine that works on text files. So if you get comma separated value files or tab separated files out of, let's say, a spreadsheet, or that's what your application is generating, then you just run this command line program called Q. You write a SQL statement and point it at your data file, and you've done nothing special to the file, and it can search that thing. Again, it might do a linear search, but you can get that up and running in just minutes versus writing a program to build data structures. So I've done that quite a bit. If I've just got data files I need to search through, and I don't really care how long it takes to do the search, I just want to get the search done. And I want to do things like take data out of multiple files and merge them together. So like you can do SQL joins in this tool. So you can take data out of one file and merge it with data in another file by joining those files together. Again, it's a little bit slow. It's certainly not as fast as a real like relational database, but it gets the job done, and I can do that in a couple of minutes. And if I only have to do this like this particular task once a week or once a day, I go with that. If I have to do it multiple times per second, I would look at something more efficient. Yeah, so the program is called Q, but I think the package is called text as data. Let me see if I can find it. Yeah, under Ubuntu, it's called Q text as data. Is there a way to use instruction level parallelism in plain C? Are you talking about like hyperthreading? So if you're talking about something like hyperthreading, there's nothing special you have to do. The compiler, and actually probably the processor, what the processor will do is when it loads your instructions into the instruction cache, let's say it loads them in, it doesn't load them in one at a time, it might actually load them in several at a time, it might load in a block of instructions. And then it very quickly analyzes those instructions to see if there's two instructions that are next to each other that could be performed in parallel. Like if one instruction is loading the number 5 into register 6, and another instruction is loading the number 10 into register 2. Well, you could do that simultaneously. So it'll just automatically put those two instructions onto separate hyperthreading cores. So they're not separate cores in that they run independently of each other at potentially their own rate. It just allows multiple instructions to run in parallel if it can detect those instructions are not dependent on each other. And there, you don't have to do anything special. The processor just handles that for you. If you want to do things like parallel programming, running your program on separate processor cores, then you do need something special. There is a library called pthread that is used to implement that. Pthread, pthread. And that's the traditional C threading library. And that one you can spawn off different threads, which will then automatically run on different cores if you have them. If your computer only has one single core, then it will run them as, I think, separate processes or separate sub-processes, but within the same core. And so then they'll run in a serial fashion, but it will look like they're running in parallel. So C doesn't have built-in parallelism like some of the newer languages do. You're talking about like Rust. So Rust has built-in parallel processing, so built-in constructs for spawning off threads. C doesn't have that, but it does have a library that's been around for a long time. I haven't played around much with Rust. It's something I've wanted to try, but could never find the time to dive into it as much as I wanted to. Now, so for those of you who don't know, Rust is a programming language that's fairly new, like in the last 10, 15 years or so. And it's kind of like supposed to be a systems level programming language like C. So it gives you access to the underlying hardware much more readily than a language like Java or Python does. And highly optimizable, kind of like C, but also has improved on many of the things that have caused C programmers trouble in the past. C has a long history of introducing security vulnerabilities in your code because things like arrays are never checked for bounds, and pointers can go off and point to something else that they're not supposed to point to. And so Rust attempts to address many of those issues. So Rust programs look a little like C programs, but they're separate. And so I've wanted to kind of play around with Rust a bit and learn more about it so that I could talk to you more authoritatively about it. But I really haven't spent any much more time than going through a few tutorials so far. What have you missed? So we're on a break right now, and we've just been talking about questions that people on YouTube are posting. Do I make heavy use of the C preprocessor? Not really. I mean, I use some defines, but I don't get much into macros and conditional compilation.
Could you go back over the Pokédex program and explain how the sorting part of that program works?
Yeah.
Thanks.
So you're talking about here?
Right, we did, I understand like this part, but how is it implemented in the main function?
So in main, we just called qsort, which is a built-in sorting function.
Okay, I had mine as the size of a Pokemon pointer, and that's why I was messing up.
So the array is an array of Pokemon structures.
Okay,
So that's why it
that
wasn't
makes
working,
sense.
right?
Gotcha. Yeah, I was getting like jumbled output, wondering what was going on.
Yeah, notice that when you put the wrong thing in there, if you put Pokemon pointer, it doesn't complain because qsort actually has no idea what the data actually is. So it's up to you, the programmer, to pass in the correct parameters.
Yeah, that makes sense with those void pointers, right?
Yeah. So there's pointers to something. So you have to teach it what they are actually pointers to.
Recording in progress.
Okay, so let's just finish up with an overview of the assignment. And those of you who are watching on YouTube and don't have access to our course files, you can actually get access to the files for this particular assignment. So the assignment is, first you're going to log into Bitbucket and you're going to clone my repository, sorry, not clone, you're going to fork my repository and then clone it. Now, if you're watching on YouTube and all you want to do is just clone it and not be able to push any changes up to my repository, that's fine. Here is the repository. So here's the address for it, bitbucket.org/profbbrown/crack3. And then you don't have to do anything with this one over here. So that's the URL for the repository. So for those of you in my class, you will click on plus and then fork this repository. That'll create a copy of the repository in your account. And then once you've done that, you're going to clone it into your development environment. So there's really only one file you need to change, and that's the crack.c file. Find the comments labeled to do, and these are the things you need to do to complete the assignment. First, you're going to write a function to read the dictionary into an array of structures containing the original plaintext password and its hash. Structure is called a struct entry. Sort the dictionary using qsort. Sort them by their hash value so that the hashes are in order. Use string compare function to compare hashes, and then search the array using bsearch to recover the plaintext password. Okay, and then this here is a link to programs we wrote in class. I need to update that with the ones that we wrote. So the ones that we just saw over the past hour or so. So I will do that as soon as we are done here. Okay, so let's go look at the programs in here. Let me just look here. Makefile, is that all complete? Yes, Makefile is complete. There's nothing you need to do there. So for this struct entry, you need to fill that in. Now, there's a couple of different ways you could do this struct. You could do it as two strings. And I know that the longest password will be 50 characters. So every password is going to be shorter than that. And the hashes are always exactly 33 characters long. 32 characters plus one for the null. So you could do it as two strings. Alternatively, since each of these are strings, as long as you have space set aside to store the actual strings, you can do them as character pointers. So in the first case, you'll have the plain text and the hash stored in the structure itself. This structure will use up 83 bytes, give or take. In the second example, you'll have to have the plain text and the hashes stored elsewhere. And then each one of these takes up 16 bytes, 8 for each one. So in this first one here, you have plain and hash stored in the structure. And the second one here, you have plain and hash, but then each one of these points to separate strings. where the actual plain text and the actual password is stored.
There's a third option, right?
What's the third option?
With making the array of pointers to the structs.
Oh, so
It's kind of like the first one, but with pointers to them.
So this is just for the entry itself, and then you're going to need an array of those entries.
Yeah.
So the array of the entries could be done in two styles. It could be an array of the actual structs, or it could be an array of pointers to the structs, where each one of the structs is, one of these things. Okay, so your data structure will either end up looking like, I'll just put P and H, right? H, P, H, right? Or it could be like this. So in the first one here, we have array of the structures themselves. And in this one here, we have arrays of pointers to the structures. Now, this second one here happens to match more closely what we did with the Pokemon. Wait, is that correct? Now I need to go look. I might be speaking out of...
I think we might have done the first one for the Pokemon. I'm not 100% sure though.
Yes, you're correct. We did the first one. Yeah. So the Pokemon example looks more like this one. The disadvantage there is that when you actually get around to sorting all those Pokemon, you have to copy like these giant structures around in order to swap them. And so if you do our plain text and our hashes, then you've got 83 bytes to swap around every time you want to sort things. So sorting might take a little bit longer, but maybe that's okay. And then in this style here, all you're doing is just switching pointers around. So there's only like 8 bytes to move around. So the sorting might go a little bit faster.
It's just because the structure is made up of pointers, right?
Yeah. The array is just made up of pointers, and you're just sorting the pointers.
Okay, so could you explain the difference between the structure as pointers and the structure as arrays, with both of them having like pointers to them? Because like you let's say you have an array of pointers to the structures, right? But those structures would either have the actual data in them or pointers to the data, right?
So this one over here would be a struct entry array of some length. And this one down here would be struct entry pointer array of some length.
Mm-hmm.
So this one down here is an array of struct entry pointers. And this one is just an array of structs.
Okay, but
what the actual struct is doesn't matter to the array. The array doesn't care whether the structs hold the hashes and the plaintext in them, or if they hold pointers to them.
Is that simply just because the nature of arrays?
Yeah. So
since you have like the first address of an array is just a pointer, anyways, right?
Mm-hmm. So you could also have this style.
Right, that's what I was wondering, yeah.
So this is still an array of struct pointers, or array of entry pointers. So both of these are still arrays of entry pointers because they're both pointing to entries.
So in short, those are really the same thing, right?
As far as the array goes, yes.
Right.
But you can see that in this picture down here, there's a lot more pointers going on because each one of these are also pointers versus storing the actual text in them directly.
Gotcha.
So this third option here is a little more complicated to set up, but if you want to try that, go for it. This second one here is probably easier to set up. This first one here is the easiest one to set up.
And do we like what's the advantage of using a linked setup in this situation?
A linked list?
Linked list,
or
yeah.
you mean like this?
No, I mean like all of this stuff aside, adding a pointer to the next struct.
Oh, I wouldn't do that at all.
No?
For this, because sorting a linked list is just horrendously complicated.
Okay. I was having a hard time distinguishing the difference between doing this and a linked list.
Oh, yeah, I wouldn't do that. Linked lists are not really designed to be sorted.
Okay.
Right, so 5, 4. If I wanted to sort that, then I would need to, like... Well,
You'd have to change the individual pointer on each structure, huh?
Yeah, like this one would have to go over here, and then this one would have to point to nothing, and this one would have to point to this one, and this one would have to point to this one. So, and then scanning through the array to look for the numbers you're looking for is like, it's going to be really slow. So linked lists are great if you need to access a bunch of data in a linear fashion. You always need to do it in a linear fashion. They are terrible if you need to look at random entries.
Okay, that makes sense.
There's just no way to get to the nth element of the linked list without starting at the beginning and scanning downward.
Yeah, I think what was it, Lab 10? I tried doing a linked list for the dictionary, and that worked okay because we were doing it linear. And so I was wondering if we were using that same technique for this current one.
I wouldn't do it.
All right.
I would. It was a good exercise because all you're doing is loading the dictionary. But in this case, because we have to sort it, I wouldn't use a linked list. That would be not a good choice of a data structure. All right, so where were we? Oh, so there's a struct entry. And then there is a read dictionary function that you give it a file name, and then it fills in the size. So you're going to replace these two lines with the actual code to open the dictionary, load each, open the dictionary file, load each line in, build the structure, hash it along the way, and then you're going to return a pointer to the array that was built.
And that size pointer is simply for the number of entries, right?
Yep.
That you want to read in?
Yeah. Well, read dictionary doesn't know how many entries there are going to be. Because the dictionary could have 100 words, it could have 1,000 words, it could have 1,000,000 words. It doesn't know ahead of time.
Is this something that you want to have as like a constant that you just set before you compile it, or
no? So look back at the assignment where we read in the dictionary, and the dictionary expanded as it went.
Okay.
So as it's expanding, you need to keep track of how big the size is.
Gotcha.
And then once you reach the end of the dictionary, then now you know how many entries are actually in it, and you can pass back the correct value. Okay, so main just calls read dictionary. You're going to pass in, we've got to replace these nulls with the actual values. So I think the first one is going to be the file name, which comes from the command line, and the second entry is that pointer to that size variable. Then you're going to sort it using qsort. Again, replace these with the appropriate values. And then what I've got here is just a single bsearch call that is guaranteed to work if your dictionary is working okay. So you will find the entry for rocku, which has this hash, if your dictionary has been loaded, if it's sorted, and now you're doing a single bsearch. So this is here kind of as a test entry, a test statement to just see if things are working. In order to get the rest of the program working, you're now going to need to open the hash file for reading and then read one line at a time and then call bsearch for each hash in the file. And it should print out the hash along with the plain text password next to it. And then finally, in the make file, you can change a few things. Just like before, you can change the number of hashes you want to crack. So you can change this to 1,000 or 50 or 2. And you can also change which RockU file is being used as the source for the hashes and also as your dictionary. So by default, it's the 2,000 file, but you could change it to the 100 or the 1,000 or even the 3 million file. The 3 million file is not stored in the repository. It's just too big. So if you uncomment the 3 million file, it will go and fetch that file off of a server and then unpack it in your environment. I think it expands out to be like 30 megabytes, which is just too big. I mean, there's no point in storing it in Git because we can always fetch a new one anytime we need it. But there is actually a rule in here for fetching that file and then unpacking it. Please don't check it in to Git, otherwise there's a lot of data to push and pull every time you want to do a commit. And also when I check out your repository, I don't want to be downloading these giant files. So don't check in that file.
So are we sorting by hash?
Yes, sort by hash. Then when you want to search for a hash, it goes really fast. Any other questions on this? So we've only got, after Thanksgiving, we've got 2 weeks, 3 weeks? I've totally lost track. 3 weeks? 2.5? I don't know. That should be just enough time.
Like
Go ahead, John.
2.5 or something.
2.5. So that should be just enough time to be able to write some simple networking programs. And what I had in mind was some programs to just measure how long it takes to send data around the planet. So I can set up some servers at various places around the planet. It's the nice beauty of running virtual machines. And we can time how long it takes data to go to, let's say, Texas versus going to London versus going to Australia.
That sounds fun.
We could even compare that to the speed of light. You can see how fast is the internet compared to the speed of light. It's certainly not faster, but is it slower? And if it is, how much slower is it? Yeah, keep in mind that when you go overseas, a lot of your data goes through fiber optic links, which are running at, nearly the speed of light. And then if there's time, we might do some other networking stuff, but that's the main assignment there for that, is the time how long it takes data to go around the internet. Okay? Any other questions? So we'll come back on Tuesday. Hopefully you've started this assignment by then, and we'll work on debugging any problems you come across. So get load dictionary to work first. You might want to put in some code once the dictionary is loaded to just print it out and make sure it's all there, and then sort it. So work incrementally through the program. Once you've sorted it, you should be able to call bsearch once and just see if you can find that one word that we're looking for. And then if that's working, you can comment out that line and then replace that with the code that actually cracks all the hashes. I think someone's asking, using a URL or IP address. We'll just use IP addresses. Actually, we'd use host names. We have a library that will translate the host names into IP addresses, so you don't have to worry about that. You can use either an IP address or a host name, and it'll work fine. Okay, well, I think that's all we have for today. So right after we end the stream, I'm going to go and update our class files so that you have access to the 3 programs that we wrote, the one for floats, the one for strings, and the one for structs, and you can use that to refer to help build your program. I will give you a little hint. You will not be able to just take your code from those sample programs and just drop it right into this. It does need a little bit of changing in order to work the way exactly we want it, but so I would discourage you from just copying and pasting. What I really want you to do is type in the code so that like the code flows through your eyes, through your brain, and then through your fingers, and then back into your eyes again on the screen, so that you kind of get a feel for how the code works. If you just copy and paste stuff, it's hard to kind of grasp how it actually works. And it's also really hard to make changes when things go wrong, because you have no idea where things are because you didn't type it in yourself. You type it in yourself, and then you want to know where variable x was declared. Oh, I remember that. That was around line 30 or so because I typed it in myself. I know approximately where to look. If you get an error that says there's a problem with the variable x, then you go, I don't know where that was because you didn't type it in yourself. So please try typing it in yourself. And you will find that debugging goes easier, and you can also make changes to the code as you go rather than having to go back and retrofit the changes into the code that you copied and pasted. Okay, so if there are no further questions, we will call it a day, and I will see you on Tuesday. And for those of you who are wanting to tune into the discrete structure stream, we'll be back on Monday and Wednesday for that. Same time, different days. Alrighty, well, have a good one, everyone. Hope it doesn't rain too much where you are. That's where I am, and we're expecting 0 rain, but not too far from here, we're expecting a little bit more rain. So, yay for rain. All right. Have a good day, everyone. Take care. Bye-bye.
Thanks, Professor.
Bye. All right, and now the YouTube folks, I have to stop your streams at different times. So, are there any questions that I missed? I don't think so. So you do have access to the assignment code by just cloning the repository that I showed you. Actually, let me just bring up the URL one more time, or I'll post it. I will post it in a comment right here. And then you can just go to that URL and fork it if you want, clone it, and then you can start working on this code. And what you'll find is that if you try it on the smaller RockU files, it goes pretty quick. But once you load up that RockU with 3 million, then the loading and the sorting will probably take a few seconds to run, maybe 10 to 20 seconds, somewhere in there, depending upon how complex your data structure is. And then cracking the passwords is almost instantaneous. Previously, we did another assignment where we did linear searches through the arrays in order to crack the passwords. And there, loading it up with even the 1 million entry file, it would take maybe 2 or 3 seconds per entry to crack them because you're doing a linear search through a file over and over and over again. So this should be much faster overall because you do all of this processing up front. You hash each one of the passwords, you load it into a data structure, you sort that data structure, and then the actual searching is really fast. And so this is more like how something like Hashcat works, where it loads in all these hashes it needs to crack. It sorts through them, organizes them, so it's easy to search through the data, and then it can start cracking them really, really fast. Of course, it also takes advantage of a GPU if you have it, and then it spreads the work across hundreds or thousands of processors. We don't have that here, but it should give you an idea about how a program like that works. Okay, so that's it for today. I will see you on Tuesday. All right, have a good day, everyone, or night, depending on where you are, and hope to see some of your progress on Tuesday. All right, take care, everyone. Bye-bye.